subject is exponents. Everyone's favorite subject. We're going back to it for a little bit. When we were in exponents last time, we added, we subtracted, we multiplied, we divided. We're not talking about any of that today. Today, we're going to be looking at what kind of graph an exponent can produce. And one of the kinds of graphs is what we call exponential growth. So the title here is Exponential Growth. And your purpose today is to be able to figure out what exponential growth is, where you see it in real life, and how does it work. And we're going to look at a couple graphs. So I'm going to set up my coordinate plane a little bit like this, and another one over here. And then we're also going to talk about some examples. So make sure you have your notes set up like that. So when you're dealing with exponents, you get a curved line for a graph. If you're keeping track of your input and output, you see what kind of looks like the curved line in a quadratic, but not really. It's a different kind of curved line. All exponential graphs kind of look similar. Like on this first one, you're going to start somewhere on the y-axis, maybe kind of like right around here. Or actually, no, let me start up higher. Maybe we'd start up here. Doesn't really matter though. You start somewhere, and then as you keep track of inputs and outputs, usually what happens with exponents is your numbers are growing, but they kind of start growing just really slowly. But then as you go further and further, they start to grow really quickly. So you end up with a graph that looks like this. It kind of comes out and then starts to curve up. And then next thing you know, it's curving up like really steeply. Maybe you've seen something like this before. They're like everywhere. You find them so many different places. Or here's another example. Maybe we start like a little bit lower on the y-axis. And same kind of thing. The numbers begin growing slowly at first, but then they kind of take off. And you end up with what looks like almost a vertical line. It never becomes a vertical line, but it looks really close to one. These are the kinds of graphs we're going to be talking about today. They're called exponential growth graphs. So places that you see this happen. Well, have you heard about the disease called measles? Measles follows an exponential growth model, an exponential growth curve. It's a really contagious, infectious disease. It's really bad. If you remember back, it was about 2 years ago around the cities here, we had an outbreak of measles, and they were really worried about it because the numbers of people who get measles, they usually start off kind of slow, but if you don't stop it, it follows this really sharp curve up. The number of people that get infected grows really fast. Another place you see this, zombies. If you've ever seen a zombie movie, as soon as you get like one zombie into a population, then it just starts to spread really quickly. That's an exponential growth. It's when like the numbers start to grow and they grow faster and faster and faster, and they just at a certain point it gets crazy. You see this sometimes with bacteria. Bacteria shows up a lot in science. You have bad bacteria that can make you sick, but you also have good bacteria that helps keep like your immune system healthy. Those generally follow exponential growth. And then there's many other examples too. So that's where they show up in real life. But let me talk more about kind of what exponential growth is. And let's go back to the measles. Let's say that one person was sick with the measles. And let's say they were at a school or in a community where there wasn't any protection. We have a measles vaccine that you get usually when you're younger. My daughters are 2 and 4 right now, and that's about the age that you start to get protected from the measles. But there was a time back when we didn't have any protection. If scientists found if one person is infected with the measles, that one person is going to infect 12 other people. So just like that, one person sick, all of a sudden 12 more people are sick. Because measles is really, really nasty and really bad. It can hang in the air. And if someone's sick in the room and you're not protected, you can come in and get sick too. Now, when those 12 people are sick, each of them are also going to infect 12 people. So you're going to get 12 plus 12 plus 12. You're going to end up with 144 newly sick people with measles. That's what an exponential growth is. It's when the numbers are growing, but they're growing faster and faster and faster and faster. Notice that every time we go up, we're multiplying by 12. So measles has a growth factor of 12. That's what we call that multiplication, has a growth factor of 12. That's what we call that multiplication in between like these stages, these steps. And we could use the calculator to find the next one if we wanted to. Because now that we have 144 newly infected, those people are also going to infect 12 more people. So if we go 144 times 12, next we'd have 1,728 people sick, newly infected. So same kind of thing happens with zombies. Once one person is zombified, I don't know how to say it, it's sick, then more people, and it just starts to grow. Bacteria, same way. And there's many other places you see this. If we want to model this with an equation that would keep track of the numbers for us, we use what's called a standard function. The standard function for exponential growth always begins with y equals, and then you have what we call an a value, and in parentheses you have a b value, and the b value has an exponent that we leave as an x. So let me show you what I mean. Let's do a measles function. World War Z. Yes, if you have seen World War Z, you've seen exponential growth. Where does it take place, the movie?
Everywhere.
Well, where does it like begin, I guess, is what I'm saying.
I think New York.
Oh, okay.
Yeah, I think it's in New York.
The one place you do not want a zombie apocalypse to start is a very city.
Yeah. So with the standard function, and you could use this in zombies or if we're doing measles, I would write y equals, the a value in the standard function is what we call the start value. It's like how many zombies or how many people had measles at the beginning. What's the starting value? The b number in the function is what we call the growth factor. I don't know the zombie growth factor. I think you could find it online though. But the measles growth factor is 12. So if I wanted to write the measles function, it would be y equals, and my start value in my example here was a 1. We started with one person sick, parentheses, the growth factor, which is 12. And then the exponent, you always leave it as an x. Because we're talking about exponential growth, some people think that like, oh, you're gonna put a number in the exponent. That's a mistake. No, you leave it as an x because it's gonna be changing. The y is gonna be changing and the x is gonna be changing. You're gonna change how many people have measles, and kind of what step are you on in the process. So the exponent's going to change and the y is going to change, and that's what creates that curving graph. Okay, if you had a number in the exponent, well, that would just be like the quadratic or something, which also curves, but not exponential growth. So that's exponential growth. That's the function. That's what it looks like. Let's talk a little bit more about using it now. And to do that, I actually want to start by sharing a video with you. Have you heard over the last year that phrase that they say a lot, flatten the curve? Have you heard them say flatten the curve, like we're working on flattening the curve?
Yeah.
So when they're saying that, they're actually talking about an exponential growth curve. So they're talking about, like in a graph, this curve that we're seeing. So it actually relates to some stuff going on right now. Ooh, Griffin says that according to a random website, zombies have a growth factor. Oh, the growth factor in World War Z is 30. So you could create a zombie equation. It'd be y equals, does it always start with one zombie? 1 parentheses 30 with an x. All right, let me share with you a video this. So click the link, make your own copy. And then we're going to go and we're going to start to edit it. There's 5 slides total. By the end of today, hopefully by the end of class, you'll finish all 5 slides and you'll be able to turn in your homework. So this takes place in April 2020, so about the same time as the video. In the video, they were trying to really figure out the growth rate back then. They thought it was maybe between 1.1, 1.4, but then doing some more research, they found that it was about 3. Since then, they found another number. It's somewhere around there. So in April 2020, scientists thought the new coronavirus, COVID-19, had a reproduction number of about 3. When a virus spreads through a population, scientists want to know how quickly it spreads. One way they measure this is by calculating the reproduction number. That is how many new infections are generated by one person. So let's complete the table. We have stage numbers at the top and the number of people newly infected at the bottom. So if we start with 1 person infected, then using the growth factor of 3, we know that that 1 person is going to infect 3 others. So by stage 1, we'd have now 3 newly infected people. And you're going to fill in your table as I fill in mine too. Those 3 are going to infect 3 more. So you get 3 plus 3 plus 3. That's going to be 9. Notice that to go from each step there, each stage, you're multiplying by the growth factor by 3. 1 times 3 gave us 3. 3 times 3 gives us 9. So if we go 9 times 3, we get 27 for stage 3. Now we're going to want to start using calculators, I think. 27 times 3 gives me 81 for stage 4. Times 3 gives me 243. And as you're using the calculator, one thing you can do is you don't have to type in the number every time. Like I have my answer here from before. If I just go times 3, it'll multiply the answer for me. And so I get 729. Times 3, we get 2187. Times 3, 6561. Times 3, 19683, and then one more, 59049. So all the situations, all the numbers we're talking about today are true. Back in April, when scientists were figuring out, okay, what's going to happen with this pandemic? How worried do we need to be? Well, this is one of the calculations they would have done. This stage could be the number of days. It could be the number of hours. It could be the number of weeks. It's whatever it is you're measuring. And so with this, notice that the table is keeping track of not how many people total are infected. It's just telling us how many newly infected people are there going to be each time. There's 1, 3, 9, 27. And by the time you get to the end, on stage 10, you get 59,049 people newly infected on that one step. Okay? So next it says, what is the algebraic equation that models the situation? Well, we see we have exponential growth. We're going to use y for the total number of people and x for the stage number. So the equations always begin with y equals, and then the number that comes next is how many was your start value. In this case, we started with 1 person. And then in the parentheses, we put the growth factor. And here we have COVID-19 has a growth factor of 3. And then we put in the exponent. And one way you could do that is with a caret symbol. And the exponent, we leave it as an x. You don't change that. You don't put a number in there. Okay, that's the equation that would create that table for you. It's going to measure the input and the output. And depending on what stage you're on, it'll tell you how many people are newly infected. Any questions, concerns? You got that? All right, so let me show you a new feature in your graphing calculator, if you have one. In your calculators, you can type in the equations, and you can get it to help you out with some of these. So let me show you how to do that. If you don't have a graphing calculator, you can still do all the calculations we do today. You're just going to have to do some of them more by hand. So now that I have my equation, what we can do is in our calculators, we can go to this y equals. It's in the top left corner. And it'll let me put in different equations. What I'm going to do is I'm going to type in the standard form equation for what we just calculated. It's 1 parentheses 3. And then to do the power, I press that caret symbol. And for some of you, that'll move your cursor up. For me, it just puts it in there and keeps my cursor where it's at. And then you can put in an X. The fastest way is by using this button up here next to the alpha. It has different letters on it. X, T, and like the circle looking thing. If you press that, it gives you an X. So there's that equation that we typed into our slide. And then if you wanted to, you could look at the graph of it. Depending on your settings, it might show up, it might not. Here's mine. So you can see it's curving up pretty quickly. But that's not the function that's going to be helpful for you today. What you're going to want to use is the table. And you can find the table by clicking on the graph button, but you have to press second first. So I'm going to go over here and press second, and then graph to find my table. And here is a table of values that should match what we had on our paper, on our slide. And then you can navigate this by using the up or down cursor. Like if I go up here, I can go up to when X was 0 at the beginning. And I can go down to the different stages. Now, if I go down, eventually I'm going to get to some of these really big numbers down here. Like, let me see if I can find one. Stage 13. They end up having to switch to scientific notation because the whole number won't fit inside the calculator. But if I want to know what it is, I can just press the right cursor. And if I hover over it, it shows me the number. This was 1 million, about 1.5 million. So that'd be 1.5 million newly infected people. Now, if I wanted to go back up, if I just try going up, it's not going to move my table back to the beginning. To move up and down, you have to be in the X values. So I have to go back to the X, and then you can move up and down to find your table. So if I go to the beginning, I can, on letter C there, check to make sure my table matches what's in the calculator, and they match. So we're good. Okay. All right, let's go on to slide 2. So we filled in our table, we wrote our equation. We've typed it into the calculator if you have a graphing calculator. And we're going to look at the table. So sometimes equations are written to find an answer to a specific situation. We need to figure out what the equation's asking, and we need to say what the answer is. So look at 4i. It says y equals 1 parentheses 3. So there's that equation that we had before. But they don't have an x anymore for the exponent. They have a 15. You know what that 15 represents? Ethan, what do you think? The stage number. So this problem is asking you how many newly infected are there on stage 15. So that's what you're going to type in here. How many newly infected at stage 15, or something like that. If you want to put it in your own words, you can. But that's what it's asking. It's saying when the exponent is 15, when the stage number is 15, how many are infected? So how can you figure that out? Well, you can either type that into your calculator and figure out the answer, or I already have a table on mine. So let me just go down to 15. When x is 15, we get 1, 4, 3, 4, 8, 9, 0, 7. See, there should be a comma there and a comma there. So that's pretty crazy. With the COVID-19 at stage 15, there's over 14 million newly infected people. That's a lot. So the next one. I noticed that instead of a y, now there's 100 out there in front. And I noticed the x is back in the exponent. So what does that 100 represent? All right, Ethan again, sure. The number of people newly infected. So what this is asking is, when are you going to get 100 people newly infected? Or another way to say that is, at what stage is there 100 newly infected? I hope you're doing these along with me. Good, I hear some typing. Remember, this is your homework today. You're going to finish all the slides. We're just doing the first few together. So if you have a graphing calculator, you just look at the table. If you don't, you're going to have to look at maybe that table we made before. Let's see, looking at it, when do we have 100 newly infected? Oh, we don't. Stage 4 has 81 and stage 5 has 243. So that means it happens sometime in between stage 4 and 5. That's what you would write. It's between stage 4 and 5. There is a way to change and go into decimals on the calculator, but we're not going to cover that today. But it might be around, I don't know, 4.2, 4.3, 4.4. It's somewhere in between stage 4 and 5. 4.4. 4.2. Oh, cool. Yeah, I thought it was somewhere in there. Now, this next one's weird. Look at this. We have a 1,000 now out in front, but we have an inequality symbol. Here's how to think about it. It's saying, when is 1,000 less than or equal to our equation? Or when is our equation more than 1,000? And the 1,000 is the newly infected. So this is asking, when is there more than 1,000 newly infected? When is there more than or equal to? Is there more than or equal to 1,000 newly infected? So when is our equation larger than 1,000? Well, let's look. Stage 6, there's 729. Stage 7, there's 2,187. So stage 7, it's too late. It already happened. Stage 6, it hasn't happened yet. So it's going to be sometime after stage 6. After stage 6. Because stage 7 is more, stage 8, everything after that is going to be more than 1,000. Okay. One more on the slide here. It says 125,000 is greater than or equal to our function. That's saying when is 125,000 more than our function, or another way of saying it is when is our function smaller than 125,000? So we would write when is there less than or equal to 125,000? When is there less than or equal to 125,000 newly infected? When is our equation smaller than that number? This could be a really important number. Like maybe once you reach that number, like the hospitals can't take the newly infected, or there's not enough testing, or this could be like a really important number here. And if I look at my table, it hasn't happened by stage 10, but it's already happened when you get to stage 11. So when are we going to be smaller than 125? Well, stage 10 is smaller than 125,000. So it's really before stage 11. So it's before stage 11. So with exponential growth, sometimes you keep track of the numbers. You do that with a table, you do that with an equation. And sometimes you have to answer specific questions like, when is this thing going to happen? And that's what's happening here. Okay? So I want you to continue on. Go ahead and move on to slide 3. Slide 3 is going to ask you about, you're going to create another table, and you're going to compare this table to the one that we made. And then you'll go on to slide 4 and slide 5 as well. This is going to be our work time right now. Let me know if you have any questions so I can answer them. If you finish slide 3, go on to 4. Finish 4, go on to 5. I have another video I'll share with you, but we'll do that at the end of class. I want to give you about, I don't know, 20 minutes or so right now to work on your homework. Okay, so work through these. Let me know if you need some help. So a question came in about slide 3. You leave the growth factor the way it is. It's still 3. They'll tell you later when it changes. It's not going to change for a while. You're going to answer a lot of questions with just COVID because COVID has that growth factor of 3. So you're using 3 again for the table. Yep, you're welcome.